Welcome to 𝗟𝗡𝗆cast, episode 124. I'm your host, Connor, and today with us we have two guests and our only panelist, as Adam mentioned before. I always mention this, therefore, I guess promoted for the time being to co-host. I guess we're going to go around and do brief introductions. We'll go over to Adam, then come back to me, and then we've got two announcements.
Right, I'm Adam 𝗔𝗿𝗆𝗆. I am head of language design and also do a bunch of other things at Dialog Limited.
And as mentioned before, my name's Connor, fan of all the array languages and host of 𝗟𝗡𝗆cast, yes. So I believe we've got two announcements. Both of them are from Adam, so we'll throw it over to you, Adam, and then we will get into today's topic.
Right, I have got good news and bad news of very different caliber. So the good news is that there's a new round of the APL challenge that just went live. So you can try it out at challenge.dialog.com. Whole new set of 10 problems. Even solving one gives you a chance to win one of the prizes. The more you solve, the better. Better chances of winning. That's the good news. The sad news is that 𝗔𝗿𝗍𝗆 𝗟𝗏𝗡𝗆, the former CEO of Dialog, passed away this past Saturday. And she'll of course be missed. She had a long APL career, and she was rightfully given the Iverson Award for propelling APL into the current times, should we say. And she might also have been a pioneer in online dating. She might very well be, her and 𝗦𝗛𝗢𝗪 might very well been the first couple to meet online ever. But there's a lot more that could be said about her, and there are episodes of various things with her that we can link to in the show notes. I'll leave it at that.
Wow, that is yeah, very sad news. I've met 𝗔𝗿𝗍 a handful of times, and yeah, very solemn news. And I guess thoughts are going out to Morten and family. Obviously, yeah, there's no, I guess, easy way to transition, but we'll do that. And
𝗔𝗿𝗍 would have wanted us to keep going. She was very practically minded on everything until the very last, and she will be proud that we keep going with this kind of thing.
Yeah. Well, with that in mind, we will conclude our announcements and transition to the topic for today, which is a new release of 𝗔. We do these, I think, annually, dating back to the beginning of 𝗟𝗡𝗆cast. We've usually brought Henry on, I think, every year, roughly plus or minus around the same time. The new releases, I think, kind of come out in March or April. And without fail, that has happened this year. 9.7 has released, and there's, I believe, 9.8 beta that is available as well. And so we have, once again, Henry Rich back with us, if you've seen the title of this episode in your feed, or if you're watching live on YouTube. And we also have a second guest, though, today. I'm going to do my best to pronounce his name correctly. We'll see how close I get. Our second guest, along with Henry, is Marcin Żołek, I believe. I didn't see too painful of a grimace on his face. And so Henry asked if we could bring Marcin on in order to help out with talking about 9.7, because I believe Marcin has been doing a lot of the work involved in this release. So before I think we start talking about 𝗔 9.7 and everything that's releasing with this release, maybe Marcin, you can introduce yourself, tell us, how'd you come into the world of array languages, and how did you start working with Henry and I guess contributing to 𝗔?
But first, I'd like to give a shout out to the whole 𝗔 team, especially Eric, Chris, Bill, and Bill, who are watching this live video cast. A few words about myself. So I'm a computer science student at the University of Warsaw. I'm in my 5th year now. In my free time, I play the sousaphone. I play it in a local volunteer firefighters band. And moving on to 𝗔, I first learned about it about 4 years ago during my first year at university.
Was that from a course, or did you just stumble across J?
No, J hasn't appeared explicitly in any of my courses, but Kenneth Iverson and the term Iverson notation has been mentioned in a few of them. So it wasn't hard to discover J, right?
Interesting. So
as J.
First year of university, you hear about J, and then what's the path from first year hearing about it to, a few years later, you're now contributing?
Well, I got interested because, well, J is obviously the last programming language designed by Kenneth Iverson, and as a more modern implementation of his ideas, I thought it's worth knowing. Just
Awesome. All right. Well, I mean, without further ado, we have, and this is the first time, so if you're listening to this in your podcast feed, it might be worth it to hop over to the YouTube channel, because Marcin has gone ahead and prepared a presentation that's going to be highlighting some stuff, and I think at some point also Henry's going to show a little bit of J code as well, so we'll swap sharing screens. So anyways, there's obviously with a YouTube video, there's always a video component, but this time we actually have a little mini presentation that we're going to see. So take it away, Marcin, and I guess we can ask questions or if they come up, but yeah, happy to hear about J 9.7. And I guess Henry's got something to add here.
Well, I'll let Marcin do most of the talking, but just to introduce the release, we have, it's good that we have video, because a lot of the work of the last year was in user interfaces, particularly ones based on browsers. Marcin will talk about that. And also, this being the first time we have video, we can mention a tool, Dissect, which is not new, but is unique and quite useful. In addition, the language-related improvements we made were related to things that are difficult to do in the standard APLs, and we'll talk about those later, particularly multi-threading and dictionary support. Marcin.
Awesome.
Okay, so yeah, we will first see what's inside the JBox. So before we dive into the new features, we will start with a quick look inside the J installation. We'll look at what it includes and what you can do with it right away. So the J installation includes several interfaces for using J, and we'll start with the command line interface, JConsole. JConsole lets you use J directly in the command line, just like other command line tools. On the screen, you can see the NeoVim with a J script and the terminal open on the right. And the script starts with a shebang, so it can be launched like an executable program. So let's run it. Yeah, and this J script downloads temperature data for Warsaw for the given date range. We pass the start and end dates as command line arguments. Well, and downloaded data are in CSV format. So J code then processes them, converts the temperature from Celsius to Fahrenheit, and creates a temperature plot. And as you can see, the script does not close the J session, so JConsole stays open and is ready for interactive programming. For example, we can convert downloaded temperatures to kelvins directly in the same session. And to return to the terminal, we simply add exit at the end. That exit, of course, can be included in the script if you wanted to close the J session after execution. Yeah, so JConsole is quite useful when you want to work with J in command line. And it also makes it easy to combine J with other shell tools. Yeah, that was the command line interface for J. But for larger projects and for learning J, we usually use a graphical interface, which is a bit more convenient. And the most, I would say, versatile environment for programming in J is JQT. So the yellowish window on the screen is called the term window, and it is a REPL, an interactive session. The second window is called the edit window, and this is where you can write code in files and run it. And when a code is run from the edit window, the results appear in the term window. And what makes JQT great is that it also makes it easy to use add-ons, especially graphical ones. Here are two plots showing examples of data visualization in J using the plot add-on. And there are many more add-ons in J. Actually, there are about more than 100 add-ons, official ones, and many more created by users. Yeah, one more important advantage of JQT is that it supports the window driver API. And because of this window driver, many add-ons can be used in JQT, not only from the code, but also through a graphical interface. And this graphical interface is especially convenient for add-ons that involve some kind of graphical output or interactive controls. And one of them is the debugger. The debugger window is now in the bottom left corner of the screen. The debugger also works in JConsole, so this previous command line interface, but only in text mode, as that was a command line interface. And in JQT, it can be used through a graphical interface, which usually makes debugging more convenient. And the debugger in JQT is also enhanced with Dissect. Dissect, as Henry mentioned, is a visualizer for J sentences. We'll talk more about Dissect later, but you can already see two Dissect windows on the screen. So the key idea is that the debugger lets you step through the program line by line, while Dissect can visualize how each line is executed. Well, that makes together the Dissect and debugger quite a useful combination for debugging J code. Yeah, JQT is also great for learning J. As I mentioned, it includes a collection of built-in labs, interactive tutorials for learning J. You can find them in menu, Help Studio Labs in JQT. Yeah, and some labs are for beginners. They introduce to J, but some of them are a great introduction for new add-ons. So labs are useful for both newcomers and just users who want to use a new add-on. Yeah, and JQT through this window driver API also supports building standalone applications in J. And one example I wanted to mention is 𝗏𝗏𝗡𝗏, developed by Professor Norman Drinkwater. 𝗏stat is used for mainly statistical data analysis, mainly in biomedical contexts. Of course, using 𝗏stat does not require any knowledge of J. J was to implement it, so it works behind the scenes and powers both the computations and the user interface. More information about 𝗏stat can be found on its website. So that would be the introduction to JQT. Another graphical frontend to J is J HTTP server, or JHS for short. JHS provides a browser-based interface to J. Henry?
I just want to stick in that JQT has been around for a while. These next two interfaces were the object of the work for this release largely. These are browser-based products that allow a user who doesn't want to commit to installing J to look at it, see what the fuss is about, and then decide to move on.
So this is separate from the playground?
Yes. There's a playground, but the playground is a little bit, it's in an earlier release. These are up to release level.
Cool.
But even though it is in the browser, JHS works similarly to JQT. It has many of its features. So like JQT, it is divided into interactive term window and an edit window. And it supports many add-ons, including the graphical debugger and Dissect. And also add-ons for data visualizations, like the ones shown on the screen. And the nice feature of JHS is that the graphics are displayed directly in the term window, just below the lines that produce them. Yes, and there's another feature of JHS that it allows you to create web applications in J. You do it like this: you define the application logic in J, and then JHS manages which parts run on the server and which parts are, let's say, compiled to JavaScript. So as a result, everything is in J, and you can build apps without thinking about what's in the front end and what's in the back end. Everything is just in J, and JHS manages the rest. And also those apps can be easily integrated with J database system, JD, or any other database through add-ons for managing databases, like Open Database Connectivity add-on. Yes, and as Henry mentioned, it is also not only available locally as a part of J installation, but also in the cloud without installing anything through the URL on the slide. And yet another interface for programming in J is Juno. Juno is also a web-based IDE that runs J in the user's browser. And the J interpreter runs as a WebAssembly module inside the browser, not on the server. But even though it runs in the browser, it runs almost at native speed. The simplest way to see how Juno works is to click the "Do you know Juno" tutorial in the right panel. This loads several short interactive chapters that introduce Juno's features. I'll maybe mention some of those features. So In the left panel, user-defined names are grouped in by part of speech. And you can see the rank of verbs and the shape, type, and the rank of nouns, and also adverbs and conjunctions. And this is very helpful while programming. It also helps explain the rank concept in J, which is one of the J core features. Additionally, when you click on one of those nouns in the left panel, Juno visualizes it, if possible, as a heat map or a bar graph. And the main idea of Juno is to bring Donald Knuth's idea of literate programming to J. This means that the program can be divided into chapters, and each chapter can include explanations written in natural language. So in a menu file in Juno, you can export and import files. And files exported from Juno are valid J programs, so you can run them without any changes in any interface. But they also include the descriptions written as formatted comments. So you can import also any J program into Juno and view it in an elegant way. I mean, divided into chapters with descriptions. And on the screen there is an example of, so you can see the edit window in JQT on the left. And it shows a J file with comments, and when the same file is loaded into Juno, then it appears in this nice way shown on the right. Yeah, and that's the end of the section on J user interfaces. For more information, obviously check the links in the video description. Most of those links go to the J Wiki, which is a great place to learn more about J. Yeah, and we encourage all users to ask questions on the J forum, obviously. So, Henry, over to you.
Okay, and bring up the next slide. Dissect has been in J for a while, but the ArrayCast has never supported video before, and it's really hard to describe something that's basically pictorial in an audio cast. So here we'll have a chance to show it off to the world for the first time. The idea of two-dimensional interfaces to computers has been around for as long as I've been doing computing. I remember Nazi Schneiderman charts and decision tables and other ideas that were going to be panaceas. In the database sector, we had query by example. And none of that really worked. It turns out that programming languages tend to be linear. But Dissect, at least, is a two-dimensional visualization of execution of a sentence. It answers the question, what did that sentence do? This is a question that wouldn't make any sense if you're not in an array language. You take a line of C or Python or something, you look at the line, you know what it does, but the primitives of J are complex enough that it is not obvious sometimes exactly what happened, particularly if something went wrong. And that's Dissect, which Marcin has been working diligently to bring it up to date with following the improvements that we had to the J language, and it's still a usable tool, and I'll let him talk about it. Go ahead.
Yeah, so yeah, we'll look at two examples of Dissect in action. Here we will use Dissect to analyze a sentence with an error. So at the top, we have the sentence we are analyzing. And this sentence creates a boxed array of shape 3. Then each box is opened and the content is incremented. So the error happens because the middle box contains text ABC. So when we try to increment the text, we get domain error. And let's look what Dissect shows us about it. So in Dissect, the data flow goes from top to bottom. Yeah, the part highlighted with the blue frame creates the boxes. These boxes contain the vector 7, 8, the text ABC, and the atom 42. And the numbers above the data show the shapes of the nouns. And the numbers on the left and right of the verbs show the effective run of those verbs. Yeah, so the array of these 3 boxes is then passed to a verb. And this verb is a composition of opening a box and incrementing its and incrementation. So Dissect detects the domain error and shows exactly where it occurred. And it shows 2 things. It highlights the item of the array which caused the error. And also it shows where the result of this item would appear in the output array. Yeah, and what's maybe important about Dissect is that it's not just a static picture, it's interactive. For example, we can select an item of the result, and Dissect shows us which part of the input produced that part of the result. And let's try more features. So when you hover over it, the matching part of the sentence is highlighted at the top. And when you click on a part of the result that was not computed because of previous error, then a nice message appears. Yeah, so that example showed that Dissect is convenient for debugging, but Dissect can also be used for visualizing algorithms and understanding what they do. So let's take a look at the maximum sum subarray problem. The problem is this: we have a sequence of numbers, and we want to find the contiguous part of this sequence with largest possible sum. And we want that maximum sum as a result. And on the screen there is an example, array C, and example implementation of the solution in J. Yeah, so let's check the result. So the result is 7. And the contiguous subsequence with this sum is 3 minus 1, 4 minus 2, 3, which sums to 7. And for simplicity, we add one assumption that if all the numbers are negative, then the correct result is 0, because we can take empty subsequence. Okay, so let's see how Dissect can help us understand what's going on here. To run Dissect in Juno, just click the line number Or alternatively, you can use a keyboard, press Control K or Command K. Yeah, so that's how Dissect visualized the algorithm. So at the beginning, the algorithm appends 0 to the array. Adding 0 does not change the result, so we can do this. This is just a small detail. The important part of the algorithm is represented by two lower rectangles. And the verbs in both of them are highlighted with a blue dotted border. And this means in Dissect that when you click on the result, Dissect will show more information about these verbs. So let's click. We'll click on 5. Okay, now the rectangle representing the verb is split into two rectangles. And the rectangle labeled final shows the result of the verb. Here the backslash dot is the adverb in J, so it means the verb performs an operation on each suffix of input, and that operation, which is performed on every suffix, is shown in the rectangle above the rectangle with label final. And here, Dissect also highlights the suffix from which the selected value, the 5 we clicked, was produced.
That's in the second box in the top, right? You can see the blue highlighting around the subway 4 minus 2, 3 minus 5, 3.
Yeah, so the rectangle is above the rectangle labeled final is again with blue dotted border, so we can click it. So let's do it. Let's click on 5 to see more information about it. This verb, by the way, is a reduction because it ends with adverb written as slash in J. Okay, now the magic happened. So a few new things appeared here. So the verb used in this reduction is a composition of two verbs of summation plus and taking the maximum with 0. Okay, so the 5 we are following from the beginning was now produced from 2 values, like in a reduction. So the result computed for the highlighted suffix, this minus 2, 3, minus 5, 3, 0, and the next element of the array, which is here 4. And the result computed from that suffix is 1, pointed by the hand, and then 1 is added to 4, and the 4 is pointed by the other hand, and the sum gives 5, which was the number we were following. So after that, we take a maximum of this 5 with 0, which gives again 5, and this 5 is actually the number we are following. Yeah, so in this way we can follow this algorithm step by step. I mean, we got to the innermost part of the algorithm, so it's a good time to to stop further dissecting. But obviously we can click other numbers, other values, and see what happens. But I'll leave this for interested viewers. Yeah, so that's it for the Dissect demo.
This is very cool. Thank you. I have been looking at Dissect a few times, and I never understood how it worked. But now I get what it's trying to tell.
It's a very complicated tool, but in general, if you want to know where a result comes from, click on it, and if it's one cell, it'll show you where that cell came from, or if it's a result of a complicated production like an adverb, it'll open up other windows to tell you what happens.
Yeah, it is very cool. I was at the same time you were explaining this. I was in Juno clicking along. Admittedly, a slightly different solution that uses the fork scan. That's my favorite spelling of it. But still, it's very cool to, like, at first you just Control K and a thing pops up. And it doesn't look nearly as complicated as this. And I was like, wait, why does his look more complicated? And then sure enough, you just click a couple times on a number. And what's really cool is, I mean, this is well, I don't know. Would you call this a trivial problem? Maybe, maybe not. But like, you could definitely, like, so when you're clicking along all the values in a scan, you know, you can see, oh, you know, it's showing you how the scan is basically working. But you could imagine for like an actual tricky problem that it's hard to visualize what's happening. It would be very useful to be able to go in here, click on some number that you're like, that's not what I was expecting, and then just trace back to the point where you realize that there was, you know, what you thought was going to happen differed from what actually happened.
Yeah, that's exactly what works. If you get a recursive algorithm, it's particularly interesting because you can go through the different recursion levels, which is normally, you know, a wilderness of mirrors, but the effect will keep track of it for you.
Yeah, I mean, it's the really, really nice feature about it is that it's interactive. Like I love and have made a video about the train trees that both 𝗔𝗿𝗍𝗀𝗏 and Dialog APL all have in one form or another, and I guess technically CAP also has something like that in their GUI. But the nice thing is that, like, you can drill down. Like the train trees are just kind of static, right? So it might give you a better ability to reason about what some tacit expression is doing. But this is like, you can actually click through and see how the calculation is happening, which, to my knowledge, I don't actually think any of the other languages have a tool like this. Adam, are you aware of anything like? I guess there's debuggers, which is close, but not this kind of.
Not exactly this. There's an operator in the defense workspace that comes with Dialog that you can, a magnetic operator, so you can attach it to any function, and it will basically do a trace on when that function gets called. It just spits out the inside succession. What was it called with left argument, right argument result? That gives you some kind of insight, but it's a very manual process to drill into things. And then, of course, this requires a full run in order to dissect, right? And although you could hit an error and it will catch that.
Yeah, it's nice as it catches the error at the point of the error, and in effect, it automatically clicks everything you would have had to click to get to the errors.
That's very nice. So there's a new thing in Dialog since version 20 of the inline tracing that allows you to trace directly into an expression without having to run it until it hits an error. And you could basically step your way through, and at every step of the way, you can inspect the current function, the primitive, and then what its left and right arguments are, and etc. That's gives you this sort of insight, but not in a 2D spelled out way.
Right.
And just I always thought I can't remember if it was something that Bob Terrio, our previous producer and panelist on the show, I can't remember if we talked about it on an episode in the past, or I've just seen a YouTube video of his on his channel. But there was another tool that I had, for some reason in my head, thought that was Dissect, where it showed a visualization of like the different types as like a different font. Is that a different tool, or do you guys know what I'm talking about? Like, or is it the same tool and it's just a different variation of it?
So no, the tool you are talking about is the add-on by Bob, and it is a different add-on, but also graphical visualization. But I think that it shows the nouns or J nouns, and it uses different graphics for different types, so that you can visualize a noun which would normally in let's say term window just shown as text, and using this add-on you can see what's the type of this using by this graphics. So yeah, it's very nice as well.
All right, so that's a separate add-on though. For some reason I had conflated along the way that because I guess they're doing things in the same ballpark, but this clearly is a I'm not sure if you want to call it much more powerful, but like this drill down ability of computations is very, very, very nifty, and I'm sure super useful in certain instances.
Okay,
right,
so maybe let's move on to the next.
Unless if there's anything else we want to say. I mean, I saw that Adam in the YouTube chat has pointed out that Dissect's been around for a while, and then one of the users, whose name I shall not attempt to pronounce, has said that maybe they should be taking a break from Prolog and revisiting J. So you have won someone over with, or potentially won someone over with the Dissect tool here.
All right.
But it's not so much Dissect, it's the because that has been around for a long time. I don't remember it not being around, but that's because I wasn't very much into
It's about
J.
10 years old.
Yeah, it's been a while. But Juno is very nice, and if I understand right, that's Marcin's work to actually make the Juno interface.
That's
entirely.
right. That's Marcin's thing.
And having it at your fingertips rather than having to write out, to dissect something or choose it in the menu or something. That's having it built in like this is very nice. I really like the being able to hover over parts of the expression, and just have the boxes in the dissect output jump around to show which parts are representing which part of the expression. It's very nice.
Yeah, web interfaces, I think I'm not sure if people underestimate their utility, but like especially for what do you call it, programming language enthusiasts. Like there's too many languages for me to like go and install like 45 different, Scala 2, Scala 3, all the array languages. And so to be able to just visit like a online REPL or IDE almost in this case is like a huge win, because I don't think I've ever played around with Dissect before, because even though I have JConsole, I've never taken the time to figure out how to launch 𝗔𝗿𝗀𝗏𝗏, or like, because I'm on Linux, I don't know, maybe I have in the past, but anyways, it's like a couple steps, and even those small steps, it's not a huge barrier to entry, but it's just like it's higher than going to a website and hitting a shortcut, right? So
yeah, that's what we thought. That's why I think it's the most important part of this release are these things that make it easier for people to get to the language.
Yeah,
it's a great language, but it does have some barriers to entry, and this reduces them.
Yeah. I mean, that's why I've always advocated for the try APLs and websites like that, because I mean, I'm biased. That's how I stumbled into them. But for someone that's just like language curious, are they going to go and download a whole thing in order just to try something out, right? Whereas, there's that threshold basically goes to 0 if it's just a website, and then you can instantly start typing around, right? It's not like they're going to become some massive user, but it just enables that what do you call it, like off ramp, like to the language. Basically, it just makes it super, super easy.
Marcin, a tiny bit of feedback here. It's very easy, as far as I can tell, to go. No, I should say it is very easy to go into Dissect.
Oh yeah, I have the exact same
from
feedback.
Juno, but how do you get out again very easily?
Every single time I hit escape, I'm like, oh, I can't do that. I gotta go hit the X button.
So it displays the window, like and on the right top corner there should be an X. You can click on it, and it will.
So I guess I can press tab and then space. Because Connor mentioned the keyboard shortcut Control-K. And then to shut it, to close the window, I can't press Control-K again. I can't press Escape. I can't.
Everyone knows I'm biased, though. I'm always trying not to touch my mouse, which is why whenever I design websites, there's always a set of secret
There's no keyboard shortcut, yeah.
for everything. You accidentally hit some key and then something happens.
We'll think about it. Okay. Okay.
But it's very nice. And I would also like a little bit more of a guide to how to use Juno more effectively. There is a do you know Juno thing, but it doesn't explain everything. Very nice.
Yeah, thanks. Well, Henry, over to you. The next part is about multi-threading.
Okay, the rest of what we have to say are language features that were added for this release. Multi-threading is not new to this release, but we have been working more and more to make it useful. You can go on to the next slide here. I think you can back up to the first line. That would be J and for a long time was a single-threaded language only, and I think that causes us to fall behind the non-interpreted languages, which the languages that declare their data. You declare an array, put it somewhere, and once it's been allocated, it doesn't move. Those languages are easier to implement multi-threading in than the interpreted languages. The interpreted languages, I'm thinking of Python and Dialog APL, as I understand it, don't allow multiple threads to run completely independently. Python, there's only one interpreter that interprets sentences. They support multi-threading in a sense that you might interpret a sentence for an IO thread that may go off and run a long time, but you don't have the threads all actually running their own interpreter and doing their different things simultaneously. But more than that, you don't want them doing different things simultaneously. You want them working on the same problem simultaneously if possible. You want access to shared data spaces. So what we've had threading for a couple of releases. What we've worked on in this release is making it easier for a single job, a single user task to be run productively on many threads at a time. So a J session can have multiple threads. The threads all share J namespaces, and they're all executing simultaneously with their own interpreter. So when we have a multi-threaded operative, if you had 8 cores running, you have 8 threads running. Each of those threads has its own interpreter with access to the global namespaces, and then they synchronize together only when necessary. In some cases, it doesn't need to be synchronized much at all. What's the next slide here? Okay, so what we've added, in particular in this release, is that the basic problem we were encountering was cache coherence. If you don't take some steps, the operating system feels that it has license to move your thread to whatever core it wants to run on. So I want to make sure we distinguish between a core, which is a hardware entity, and a thread, which is a flow of execution that has a J interpreter. And theoretically, any thread can run on any core and get the same result, but it won't have the same performance, because what's vital is that each core needs to run as much as possible in its own internal caches, at least level 1 and level 2 caches. So what we'd like to have is a big problem in which threads are tied to cores, and in particular, each thread gets tied to a subset, an unchanging subset of the overall problem. And if you achieve that, the level 1 and level 2 caches of each core have persistence from one call to the next, and the program can operate without expensive accesses to shared memory. So we allow a thread to be bound to a specific core first, and then the thread can be assigned to a locale. And that locale will have enough information to tell that thread what part of the problem it's working on. When you have that, then you can launch a user task all at once. You can say, here's a task, do this in multiple threads, and each thread will take its part of the problem and return its results. Next slide there. As an adjunct to that, we have a way, we've added a way to force a noun to be not aliased and not copyable. So we call it anchored. We can anchor a noun that will force a noun to stay in one place, and you can only modify it in place, but multiple threads can modify it in place simultaneously. So it provides an easy way for data sharing between the different threads that are being used to solve a problem.
That does not mean that threads can like stomp on each other.
Yeah, don't do that. It won't crash.
No, we'll just get garbled data.
But if you have a communication area, you anchor that and then tell each thread to work on a non-overlapping part, then they might be accessing the same noun value simultaneously, but they won't corrupt each other's access. If the regions overlap, then they'll corrupt each other's access, and you'll need to debug that. But anyway, if you do all this, the cache for a thread stays hot when the thread starts executing, and the thread can pick up execution without having to transfer from off core. I have an example of this. Let's see, I'm going to try to share my screen here. Okay, so here's a bunch of code. The first half would just be in a library, so you can ignore that. The code starts here where I'm hovering, where it says the code. We allocate a result area of 1,000 integers, and then anchor it to memory. So that says this result area is going to stay put. And now we're going to run a program, and here's the program. You know the 𝗏𝗏𝗆𝗏𝗏 conjecture?
Yeah.
It's pretty cool. It says you take a number, pick an integer. If it's even, divide it by 2. If it's odd, multiply by 3 and add 1, and keep doing that. Eventually, so the conjecture goes, the result will be 1. So that's what this is doing, is applying that to various integers and counting how many times it went through the loop. So here we have count the number of loops through the 𝗏𝗏𝗡𝗏 conjecture for one value. So as long as the value has not got to 1, you do what I said, increment the count, and then do what needs to be done, whether it's even or odd. And the second program is just a loop through doing that. So X, the left-hand argument, is the start of the interval, and the Y is the number of values. And it just does a loop calculating the count. So the only thing I've done that's not just vanilla J here is I anchored the result area, and I'm using something called an atomically modifiable value, which is like an integer, but it can be modified by multiple threads at a time. So you can add, if you want to subtract 1, you add -1 to your atomically modifiable value. So here I'm using extended arithmetic, so 3 to the 1,000th power, whatever that is, that's some 500-digit number, and we chose the result area to be 1,000. So we're timing the execution of this sentence, which calculates the 1,000 𝗏𝗏𝗡𝗏 values. I like to use this when I'm burning CPU time because it is a conjecture, and it's possible that it might have never completed, and we'd win $1 million, I think, if we could disprove the conjecture. But unfortunately, the conjecture turned out to be valid again. So it took 16 seconds to do that. The result area is all the values. We can get an idea for how much computation is doing. So like 11 million computations, each one of them doing rational arithmetic on 500-digit numbers. That's a respectable performance. So say I want to run this on multiple threads. This is what I do. All I have to do is say, do it on multiple threads. And regrettably, I'm running 8 threads. I got about a 3x performance increase, mostly because, all right, it's about 5x, except that running this screen sharing, running this video call takes so much CPU that the improvement isn't as impressive. But the key thing is, this is all I had to do. I added the all threads. That says is run this as tasks on a mask of processors, and the same program. It ran the same program in multiple threads. Ran faster. Now the result was the same because in the first time I ran it, I had one processor computing all the values. The second time, I had 8 processors computing values and storing into different positions, but they each store into the right spot. So I get the right answer. It's just, I don't think it could be any easier than that to run your program in multiple threads. That's what we've been working on for multi-threading in 9.7. On doing this, I've learned some interesting stuff about multi-threading. You say, well, let's start 8 cores. How much faster should it run? Here it ran somewhere around 2.5, 3 times faster. Usually it runs 4 or 5 times faster. Why doesn't it run 8 times faster? Well, one is that I'm on an Intel machine, and the E cores have a slower clock than the P cores. But the other one is that as you run more cores, the chip gets hot and the CPU slows its clock speed down. So if you're going to be serious about running multiple threads, I think you need to enlist the help of a gaming enthusiast to buy you a cooler for your CPU so you can get maximum performance. But before you can do that, you have to have a language that supports multi-threading, and that's what we're continuing to work on to make J that language. I think you can pick up now and march on dictionaries.
Would you like to make an introduction to dictionaries, Henry?
Let me come in after you've given the old-fashioned J pitch. And dictionaries are not a way to do something new. It's a way to do something so much faster that it amounts to being new.
As Henry mentioned, dictionaries are not a completely new idea in J. J has always had search primitives called the 𝗦𝗢𝗢𝗏 family of verbs. And the way they work is one of the ideas behind the design of the dictionary add-on, which is new in J 9.7. Before looking at dictionaries in the new add-on, we'll take a look at one of the search primitives, and we will take a look at the primitive dyadic 𝗦. So this primitive finds the position of the first occurrence of the right argument y among the items of the left argument x. So suppose we want to find the position of the first occurrence of 5 in x. So we just write x 𝗦5 and get 4 as a result, because 4 is the index of 5 in x. And when we write x 𝗦7, then we are searching for a number in x that does not occur there, and we get the result 9. So this is because if the searched value doesn't exist, J returns the length of x, and the length is just one more than the maximum valid index. And this idea, that was the introduction, and now it can be generalized for not only atomic right arguments. So if the right argument has a higher rank than the items of x, here it is an array of shape 2, then the operation 𝗦 still makes sense, because it just means that we want to perform multiple searches. And here each cell of y, the right argument, with the rank of the item of x, is searched separately, and the indices, the result indices are assembled together into an array, into the result array, and the result is array for 9. Yes, and we can generalize it for higher rank arrays. So, for example, here x is an array of shape 3, 3, and it is filled with integers from 0 to 8, because we use 𝗦 in monadic form. And array y is here matrix 2 by 3, shape 2, 3. So this means that we are doing two searches. First, we search for the array 3, 4, 5 into in X, and it occurs at position 1 in X, and then we search for array 2, 1, 0, which does not occur in X, so the result is 1, 3. 1 because 3, 4, 5 occurred at position at index 1, and 2, 1, 0 didn't occur, so we get 3, the length of the X. Okay, so that was an example of I dot, and going back to dictionaries, we can use it for a similar functionality. So if all our keys and values can be computed before all the searches, then it is sufficient to use dyadic I dot. For example, here we define keys and values, and for simplicity we just define values as keys plus 10, just to make the example easier. So we define verb get, which searches position of argument in keys. This is the right part of the fork, and then selects from values. Yeah, so here you can see that get for 9, 2 returns correct result, which is these values plus 10. And what is interesting here is that internally the definition of verb get creates a kind of dictionary in JNG. This hash table is built into the verb during its definition and used then for all searches, which is very efficient.
So just the assignment itself could potentially be slow.
Yes. You're talking about line 3, get equal colon, right?
Yeah.
Yeah, the keys, ampersand I dot, that is what creates the hash table.
Right. There's a similar thing in dialog APL with the bind operator, but it doesn't compute the hash table until you use it.
Oh well, yeah. This is the big improvement. If your keys weren't changing very much, then this is sufficient. You don't need a dictionary, because that lookup will be very efficient.
No, it's the same. It's just J is eager, right? As soon as you make that assignment, it detects the composition of keys and I dot.
Oh, I see. Yes,
and computes the hash table, whereas dialog is sort of lazy and it just composes it, and then when you run that function for the first time, it stores the hash table.
Okay, right. Yeah, we do it. We figure
you have to prime it.
Yeah. Okay.
Okay, so yeah, that's very efficient, and so we can use the I dot primitive for some kind of our custom dictionary, but sometimes we cannot divide the algorithm into these two parts. The first, setting up the dictionary of all keys and values, and then performing all the searches. I mean, sometimes search operations are alternated with updates, small updates, for example, and this scenario, so queries alternated with updates, are the scenario that dictionary add-on was made for. So let's start with some examples of the new dictionary add-on. So to use the dictionary, we first need to load it. So we write load. Okay.
I just wanted to stick in a few words. Everything you've said is just right, but the key thing here is that when you have an application where the mapping changes frequently and is large. The standard Iversonian methods just don't work. I mean, they work, but in that example we had where you did the keys ampersand I dot, it has to create an entire hash table. If you've got 1 million values and you modify 10 of them, the hash is going to calculate all 1 million values. And that leads to intolerably slow performance, to the point where there are times where you have to change your algorithm because of the speed of the speed or slowness of the primitives. And that's a signal that the language needs an improvement. That this dictionary idea, well, generalized, it's the concept of a mapping. Computer scientists talk about ordered maps, unordered maps, ordered sets, unordered sets. This is a basic need in the computing biz, and so it justified creating a separate facility that doesn't use the normal language facilities. A dictionary is an example of a shared modifiable object. It can be used many places. It accepts changes, it remembers the changes, and allows incremental changes. And we're talking about, it wouldn't be unusual to have 100 million items in a map. And we want to be able to support dictionaries of that size efficiently.
Mm-hmm. So the keys and values in the dictionary may differ in type and shape, but all keys must have the same type and shape, and all the values must have the same type and shape. And this is exactly like in the example with I dot, where keys and values were arrays. And well, this is not a limitation, because you can always box the keys or values, and the shape then the shape of the key will be empty, and the type boxed. So that's okay. Yes, and let's create a dictionary. So to create a dictionary, we create an instance of the 𝗔𝗿𝗏𝗆 locale and pass construction parameters. And the only required parameter is the type of data structure used by the dictionary. As Henry mentioned, there are two types, two options here, hash and tree. So hash is a little faster than tree, but tree provides an additional set of verbs, verbs for range queries. So the usage is exactly the same for both of them, the hash and tree, unless you use range queries. So unless you use them, you can change hash to tree or tree to hash at any time, and it will still work. So that was the required parameter, and all the other parameters are optional, meaning that they are set to their default values. So, for example, here we create a tree dictionary with all optional parameters set to their default values. And we write just tree connu 𝗔𝗿𝗏𝗆, and this creates a locale. And here we assign its identifier of a locale to a name. For example, here D, to use then this dictionary. And I said that all the optional parameters are set to their default values, and by default, keys and values are integer atoms, so they have rank 0. And to use different shapes or types, we use key type, key shape, value type, and value shape parameters. We also have shorter abbreviations of those names. You can check all the documentation for the details. So, for example,
can it not just detect the types once you start adding data to it?
So yes, like specifying the shape is nothing new, because to create a multi-dimensional array in J, we also say what shape it is. But yes, here we also specify the type.
I think it would be dangerous to infer the type, because a user might install a 1, which would be inferred to be a Boolean.
I see, yeah.
Turns out to be something else. So you have to give it the type.
I mean, it could at a performance cost, it could go and upgrade the type later if it then sees that it wasn't right.
But if isn't that type, you got 100,000 items in the tree, and then all of a sudden somebody gives you a rational.
No, I understand. For ease of usage, it would be nice, but of course, for ease of use at the cost of performance, you could just use the boxes, so then everything's fine.
That's true.
Yeah, so here in this example, we specify that keys are free by matrices of shape 3, 2. And the value type of the values is rational. So the keys are here integer matrices 3 by 2, and values are rational atoms. Here we don't assign this new dictionary to a name, because we will stick in further examples with the default case of integer atoms. So yeah, let's put something into the dictionary. So we use a verb put, and the right argument is the keys, and the left argument is the values. D is, as you remember, an identifier of the locale of this dictionary. We assign the identifier to this name. So to use this verb from the locale, we write a double underscore. That's how it's done in J. And now to retrieve the values corresponding to keys, we use verb get. We also define verb get in the 𝗦𝗢𝗢𝗆 primitive example, and this is very similar. So the right argument here is the keys to look up, and the left argument is here optional. So it specifies what to insert in the result if a key is not found. And here, for example, dictionary does not contain key 7, so the third line returns -1 in the index 1, the last position. Yep. So yeah, this is very similar to what we did with dyadic 𝗦. But here, when using this dictionary add-on, we can also easily put and delete keys at any time. So yeah, we here after the get, we then put, delete, and can after that again get and query the dictionary. Yeah, so we specified the dictionary's type as a tree, but everything shown so far is exactly the same for hash. So I mentioned that what Tree Dictionary additionally offers is queries, range queries. So these are queries about order of keys. And there are quite a few of them, but here we will just show two examples. So here verb min returns array of two boxes, and the first box contains the minimal key, and the second box its corresponding value. And the second here example verb is after, and it returns at most x. X is the left argument. So at most x keys, and there at most x keys which value, which values are greater than y. Y is the right argument. Yeah. So that's the basic introduction to dictionaries, and well, various algorithms using this add-on have been discussed on the J forum, and these examples are also included in the add-on documentation in JWiki. There are full implementations of these algorithms with examples ready to run. Yeah, and also interesting use cases of these dictionaries have been shown at New York City J users group meetings. And yes, I think this is a good moment to invite everyone to New York City J users group meetings on behalf of Devon and McCormick. You don't need to live in New York to join, because all the meetings are held remotely. And the next meeting will be on May 12th. So see you there. Yes, so would you like Henry to add?
I have a quick question before, just on the last slide. Is the suffix __ d, what's that about? Like, is it necessary, or does it indicate something?
Think of it kind of as d.get, d.put, d.del.
Yes. Yeah.
In other languages.
Yeah, the double underscore is read in after nd, or you could have __ d __ e, which would be after nd in e.
I see. And is this
Or
like a convention, or it's actually like syntactically, whenever you see this, it goes and grabs that from the dictionary library?
No, it's not. This is a language feature. It's much lower than the add-on level. Any verb, any name can be qualified with __ locale name, and that allows you to distinguish different values of this, different
Gotcha.
entities with the same name.
Okay, yeah. So it is essentially what Adam said. Yeah, just like
Exactly. Yeah, it's a namespace. D is a namespace. Do you know about underscore, like name _ dict _ says in the dict locale. It spells out the locale that it's in. That's called a direct locale specifier. This is an indirect locale specifier, where D is a noun that tells you what locale to look into.
I see. Okay, that makes sense.
Though I'm a bit confused about the exact syntax for it, because the examples I see at the JWiki is like _ locale name _.
That's direct locale. There you spell out the locale. If you used after _d _, you would be looking in the locale named D, exactly D, the letter D. Here, D is a variable, probably containing
okay, I see. Okay,
this is how you do objects. If you think of it, D is an object number.
It's a quoting unquoting mechanism. Do I want the reference that's called D, or do I want the actual thing that has the name D. That's how you
That's right.
distinguish between.
Yeah.
Okay, sort of like the left side of the assignments, where you can quote them and
Yes.
parenthesize them to sort of say, evaluate this, and the name that it evaluates to, and that's the name I want to assign to.
Yeah, generally in J, when you think of object programming, an object is a locale, is a numbered locale. So it's identified by a number as opposed to a name locale. Like the dict add-on is in the locale JDict, but the objects created by it will be numbered locales that exist in the locale namespace.
Right.
And use a double underscore to reference an object.
But can you nest them then?
Oh yeah.
That's
what I was saying. But underscore D underscore E means first look in E,
like
and then look in D inside E, and then look at
the E that's inside. Yeah, okay. Yeah. So the value is the names, one of them. Yeah. So it's very much like the dot when you write it like this.
Exactly. That's it.
But opposite direction.
Right.
Or colon in C++ or something.
Yeah, maybe. Yeah, it's been a while. Let's get to that last slide, Marcin.
Yeah, well, the colon would be, I think, for these locales, so they are equivalent in J to underscore locale name underscore, and
I see.
More like an object.
I see. Yeah. Whereas the normal dot thing in most languages is like the just evaluates that thing. Yeah.
Okay.
I think.
So to tie it all together, our work, dictionaries and multi-threading. Most dictionary implementations that I know of do not implicitly take note of multi-threading. Some designers have even suggested that you should keep it that way, but you pay a heavy price if you do, because if a writer has to block all the readers, one writer can cause a huge hit to the performance because all the readers have to stop. Our dictionary implementation is designed to work with our multi-threading implementation also. In spite of that, all the reads and writes are atomic. So if one thread writes a block of data, that block is available, all or none, to any other readers. And what we do for performance is a rather complex locking system. Basically, the writers first arbitrate among themselves to choose one writer at a time, and from that point on, the keys and the values are locked independently, so that when first the writer gets most of the writing done without any lock at all, and then implements a very brief lock on the keys to update the keys, releases that, and then takes a very brief lock on the values to update them. And the result is that even if you have a writer that's writing as fast as it possibly can, the read performance is hardly affected at all. And even if you have two writers, the read performance is affected just a little bit. This is good enough that if you've got a multi-threaded application and you have your threads need to talk to each other, a dictionary is not a bad way of deciding to do that. Just create a dictionary and let them put keys and values into it and communicate that way. I think that's what we got.
All right. I mean, there was, well, actually, I was going to say at one point, I guess this is like a trend, right? So, I mean, Q and K have always had dictionaries / tables, but now J, I guess, has them. Cap, I believe, has them. Tiny Apple has them. And that and I think actually BQN added them a year and a half ago or half a year ago, and they were working up because it had been like a request out of the advent of code. And Weewa has, actually does Weewa? So it might be Weewa and Dialogue, although the Weewines are going to skewer me if I have misremembered that they do or don't. I know they have the memoize function that enables, or I'm thinking of the path tracing. Anyways, maybe someone in the chat will comment on Weewa. And speaking of the chat, there was a question that I read and then failed to ask when you were talking about fixing the memory locations of the threads. And Hans asked, does that mean that in theory you could modify a different column, different columns of the array at the same time using...
Exactly. Yes, that's what you can do. I mean, you can also modify the same columns, but then you'd have to make your own decision on how to decide which is winning. But if you just allocate different columns or rows to different threads and they properly, each one stays in his lane, yes, that's exactly what the example that I put up did. Each thread, after it computed a collapse number, stored that thread into the array at the proper index.
So that is rather useful if you've got some computation where
yes,
you're
it
doing
is
independent things.
It's pretty tough on the interpreter to support it, but
I mean it's tough on you, right?
Yeah, I was gonna say it's tough to implement, but luckily that's only for I guess the J team. Everyone else that gets to use it just benefits from that work. So
that's the power of these types of languages, right? They are hard to implement, but the benefit is to the user.
Yeah, I always wonder about the I think about how Arthur Whitney is the one that always comes to mind, but implementer infamously of all the different Ks, and I always wonder what percentage of the code that he writes in his lifetime has been C versus K, because he's writing the implementer, and I guess it's the same for you, Henry, and you.
Yeah, I don't write as much J as I would like.
Yeah, that you would think that the implementers are the foremost authorities and experts in these languages, but they actually percentage-wise potentially end up writing more of the implementation language than they do in the actual language. But I don't actually know. I'm not an implementer.
Well, I think that might be right, but
that's the case. Yeah, for sure.
I was a J user for about 20 years and wrote some pretty big packages, so I got a good idea of what the language needs before I started fiddling around with it.
Oh yeah, it wasn't to question your talent for J code. I meant more just as like you'd think that the implementer spends all their time writing J because that's their favorite language, or they really like it. But in fact, they're actually writing more C code on a day-to-day basis, or whatever the implementation language is. Because that's actually what it entails. Unless I guess there are certain things that are written. Was it Adam? You've remarked on, was it Roger or someone that most of their work actually was in the language. Like there's features that aren't always library stuff that's implemented in whether it's APL or J and not actually the source language.
I mean, in Dialog, there's a bunch of stuff that is implemented in APL, but that still drowned out by the amount of C code.
Yeah,
of course it is.
In J, Roger very cleverly, in the support for sparse matrices, I'm thinking about that's not exactly written in J, but it almost is. It's written in internal subroutine calls to call the J functions. So that the sparse matrix works for all different precisions. You can have sparse booleans, sparse rationals, sparse anything. Most of it is being processed through higher level J verbs.
Right. I think that's
We all, also a lot of J add-ons are written in J, or fully or at least partially to communicate with some external software. But yeah, add-ons are the place where there's a lot of J code.
yeah, good to know. All of which are now available via Juno. Is that accurate, or was that JHS, where you can access the add-ons?
Where you can access the add-ons in well, the most of the add-ons are available in JQT because of this window driver API, but JHS also supports almost all of them. And in Juno, yes, also you can use some of them.
Okay, yeah. So all three. All right. Well, I mean, we can ask the chat. Although a couple questions already were asked. If there's any final questions from the chat, now's the opportunity to ask either Henry or Marcin. Adam, do you have any final questions? Or I mean, should we ask anything about? Is there 9.8 beta? Any preview of what's going to be happening over the next year? Is it going to be more enhancements to Juno and the UI stuff, or is it too early to tell what the next year is going to look like?
Marcin is the only one that knows Juno, what's going to happen to Juno. We haven't decided. There's this thing I've heard about called AI that I'm thinking might be worth getting into. I don't yet know what effect, if any, that would have on what we should be doing, but we'll certainly be looking into that. We have a lot.
When you say AI, do you mean using AI to implement stuff, or do you mean putting some bells and whistles on J to make it a language that is favorable with like LLMs and stuff like that?
Well, that's the question. If we could use it to write code, that would be interesting. I haven't had particularly good luck, although it does a good job of going through the code base and summarizing things. And in a couple of cases, we gave it some bug reports to look at, and it got into the subroutine that needed to be fixed, although it didn't get the fix right. But I'm more interested in what we can do to make it easier for our users to use AI to write J. And I have no idea what that is. Do we need to write more code to help train the AIs? Give it a better set of code to look at, or do we need to add anything to the language? I think probably not modify the language much, but we need to be thinking about it anyway. It's clearly an important development in computing.
Yeah, there's some article I can find later that was measuring the density of like LLMs trying to generate code, and I can't remember if, like, in the languages that they looked at, Clojure was like winning, which is a Lisp, and then they added a couple updates saying that like a bunch of people have mentioned APL as like, oh, how come you didn't look at this? And they just weren't aware of it. But they said that because of like the Unicode characters, it actually didn't, because the code points or however that works. But then someone followed up and was like, oh, what about J? And they redid their little study and or program that they were measuring, and J won by a long shot. And like multiple people have pointed this out to me. One was on Twitter and one was on LinkedIn about how J could technically be like the most efficient way of representing certain programs because it's ASCII and it's an array.
Yeah, wasn't there a big push a couple of decades ago about getting rid of the programmers and having subject matter experts write code in APL? Because and I think maybe that foundered because it turns out software engineering really does have an engineering component, or at least it's a very skilled trade, and you can't just let your subject matter experts loose on production code. But with AI, might that change? Might it be that you really could have a user, a non-programmer user, getting something useful done. I don't know. I think we should be looking into that for the next year.
Well, I think that generating like explicit definitions using those whiles, if conditions would not be difficult, because generating code even in J using them is very similar to other programming languages. But what's difficult is to generate a good J code, which really shows the way of thinking in J. So
I will. Maybe some people will criticize me for this, but I think in general it'll be difficult for so what is today called AI, but better called generative AI or even LLMs, is to generate code that shows thinking, because they don't.
Yeah, they don't. But I was looking at a couple of physics type problems, and I've reached the conclusion that with AI, you've got a system that can solve any problem that anybody's done before that it can find an example of. Okay, so maybe it doesn't think, but I think about the students that I taught in high school. You know, just being able to solve every problem they've seen before was all they aspired to, pretty much. You know, is this going to be on the test? It turns out if all you could do is solve every problem, you may not have an advantage over the AI. It's hard to know where this is going to go.
It's a whole different subject of what's going to happen when people don't have a chance to learn and so on. But yeah, I think, I mean, if you want these generative systems to produce reasonable J code, you have to publish a lot of J code. And of course,
I think that's right.
Of course, publishing a lot of J code makes little sense since J is so compact, just like any of the other array languages. So there will just be less code.
Right.
I also think there are various fundamental issues that the same code can do many different things in most array languages. Right? There are generally no hard types, and things are polymorphic in various ways, and that's a problem for these systems, because, as you say, they just munch a huge amount of data and spit out something that is composed from bits and pieces of everything that's been munched up. But the more specific things are, basically, that's metadata. The easier it is to retrieve that. But if you've got code that is universal, it's not very easy to identify what exactly is it for. It can be used for multiple things, and I think it makes it harder for these systems to retrieve the right code for the right situation. Right? It can't just use types as a hint to needing this code over that code. It can't just use descriptions of intermediate variables and so on as hints as to what it needs to be retrieved, because the names that array programmers will use will often terse and not very obvious what they mean. They might not mean anything very concrete, or they might be very general, because the code can be used for so many different things.
Or you may have a partially tacit line of code and the names don't even exist.
Right, exactly. And for tacit things in some of the languages like APL and J, they will generally mean two different things, right? The same code. Right. Whether you're using it phonetically, dialectically, and it's not obvious from context. And not being statically parsable, this makes the problem even worse. Out of context, you might not be able to tell at all what the code is supposed to do. All of these things make it harder.
It does, but the models are very resourceful. For example, we might say, okay, it turns out what we need to do is put the word monad or dyad at the beginning of every verb. You know, give it a hint, and maybe a few coding practice changes would make it easier for the LLMs to make use of our code.
So I think what could help is annotated code, right? Code that with a description as to what it does. Just like these systems needed for a long time images, with people annotating what's on the image in order to learn to or should we say, to fake it, to be able to identify things on images, seeing the patterns, and later generate those things as well. So too, they need annotated array code that says, okay, this, when you see this, that you can sort of infer that that has to be called phonetically or dyadically. And something I have in 𝗟𝗡𝗆𝗆 is having the same entry multiple times with different descriptions, because the same code can do all these different things that are not obviously the same thing, even though the APL code is the same thing. And so having multiple descriptions on the same code can help those hint to such systems that, yeah, this is the right code for all these different problems.
Yeah.
There are, I guess there's one question. Well, I mean, there's two questions in one comment, but for the first question that Max has asked, what's the style of C code? You can technically just go look at the open source J GitHub. And the other question is maybe unrelated, but are there any future plans to make the JBuild/install system more friendly to foreign package managers, and maybe make Pacman, in parentheses, JS1, support user setting paths?
We have a work item on the GitHub issues list, and if you have any, I don't do build tools at all. They terrify me, but we have people who work on them, and if you have suggestions, I'm sure they would like to hear them, because we do want to make sure people can build J releases.
Okay.
Mm-hmm.
And the one comment is from Hans. Personally, I would love to have videos about small problems and solutions in J. I've read much about J, but some videos like Adam's for dialogue are very helpful.
Okay.
Which I think, I mean, Bob Terrio has his YouTube channel, although I don't think he is posting new videos. And that channel, I'm not sure how discoverable it is, but definitely if you search his name on YouTube, but potentially you haven't stumbled across, or actually I can go find the link and put it in the chat. But I know that there is at least Bob's channel where it's not exactly the same style as Adam's videos. What was it APL Quest? Was that the name of the series that you did for all of those problems? It's not exactly like that, but it's still might scratch the itch that you are looking for.
I think we have like a crossover of concept problems between APL and J. APL has got a ton of very simple problems being solved and explained, and J has fewer of those very simple ones and more of the larger lab type things that are available. Those are missing in the APL world. Doing something more with APL. So maybe we should cross-pollinate.
Yeah, sounds like it.
Yeah. All right.
Because obviously a lot of the things that APL will be good at, J will be good at, and vice versa. This is the nature of things.
Yeah.
Connor, one thing you mentioned before was 𝗏𝗏 and dialog not having dictionaries. I don't know about 𝗏𝗏. At dialog, we're sort of reluctant with regards to dictionaries because we've got namespaces already. So namespaces are like the locales, and as you can see here, syntactically the J dictionaries have sort of been built as locales on the locale system and the object system.
That's not really true. We access the dictionary through an object, but the actual work is done through foreigners that bypass the usual protections on an object. So it normally, if two different threads modify a noun, something bad's going to happen. One of them will overwrite the other. But for the dictionary, there's not a specific dictionary data type, but we access only through functions that know to take locks and protect against problems. So it's a pretty big change. It's a big step up from just having a namespace.
Yeah, so that's the thing. Dialog already has these namespaces, and that means it has the syntax that you might want to use for the dictionaries. The problem is that there isn't an efficient and general dictionary support built into the system that could be added in the same sort of way, where we pretend things are namespaces, but they actually dictionaries. So you have some kind of way to tell the system, oh, this thing that looks like a dictionary, it looks like a namespace, that's actually a dictionary underneath the hood. There has been some proposals to do something called magic arrays, where you sort of define a class that and how it should behave outwardsly. And you can, to a certain degree, you can already model this today, but you have to build it up yourself. So there is definitely room for such a thing, because namespaces are slow in there to use as dictionaries, and they're not general. You can't just use any value as a key.
There's
Well, so I wanted to ask one more thing about the dictionaries. Oh, right. Notation. So what's next? Just like APL got array notation, maybe J needs a notation for the dictionaries, so you can write them out, right? Instead of constructing them piecemeal.
I don't understand.
Right now, if I understand right, you can't write a dictionary, right, in J. You can only construct it.
Well, when you say write, you mean
like a literal dictionary, the way you can write a literal character vector, and you can write a literal numeric vector, but you can't write a dictionary, right?
no, you have to. We have load and unload verbs. You can take everything in the dictionary and collect all the keys and all the values and dump them into an array, and
Right.
vice versa. But in general, since the dictionary is just a key value combination, if you give it all the keys and the corresponding values, you have constructed the dictionary. And for a hash map, that's as fast as anything. For the ordered maps, it uses a faster method if you tell it the keys are already sorted in order. So it can generate the search tree directly rather than having to go through nlogn operations. But that's the equivalent to bulk load and bulk unload in a database environment.
And there's one last question, I guess, before we wind this down. And that's from Hans again, asking, are there any conferences where J talks can be found from time to time?
Where's our Raycon, Connor?
Yeah, I guess we all know the answer to this question, is that currently in 2026, there unfortunately are not any that at least I'm aware of, unless if there's some secret conference that somehow is slipped by not just me, but the entire Arraycast panel. There used to be the J software conferences that I think ran up until the 2000s. Maybe there was even one in like 2010 or 12 or something. But those do not run anymore. And the closest probably you can find, unfortunately, are the talks that I have given at random functional conferences that are not about J, but they mention array languages in general. And yes, Adam was referring to the fabled, the mythical ArrayCon that we have always talked about having. And at one point, I think actually Steven, former panelist as well, he had gotten kind of the motivation to maybe do something like that, but then I think it just ended up turning into another Iverson College. Was it Iversonian? No, Iverson College? Yeah.
Iverson College, yeah.
But yes, I mean, if I somehow magically get a bunch more free time, it would probably start just as a virtual conference. And the idea would be that, we'd invite some people for maybe the first edition to give, a J talk, an APL talk, a WeWa talk, etc. And then if that went well enough, potentially try to organize something in person. But it's a lot of work to.
Iverson College wasn't that, in my opinion. it's different. It's a get together, but less of a conference
it's
feeling.
an unconference technically.
Yeah.
There's no scheduled talks. There are talks given, but it's like very informal. Anyways, and even better than us organizing one, it would be if someone out there just did all the hard work, just like Henry and Marcin and the J team have done all the hard work on the J interpreter. If someone else wants to set up a conference, I think we would all be very excited for someone else to take that task on. I would love to do it if I had more time, but unfortunately there's not enough hours in the day. Anyways, I think that is concluded all the questions in the chat. Thank you for everyone in the chat for attending live and contributing to the discussion. And most of all, thank you both to Henry and Marcin for coming on. I'm sure at minimum we're going to have potentially both of you back on in a year, if not sooner than a year. I think usually we've had Henry on to talk about different topics, tacit in the past. We still have the contact@𝗟𝗡𝗆𝗏cast.com email if you want to reach us to us there. But we also, we don't plug it very often, but we do also have a Blue Sky account if you just want to message us there. So there are many ways to get a hold of us. And yeah, thank you both once again, Henry and Marcin, for coming on and making this awesome presentation. It's probably been the first, if you count it as a talk or a presentation, first J talk in a while since, I know there's the famous Tracy Harms, I believe is his last name, talk that is floating around on YouTube, but maybe this is the first one since then. So yeah, hopefully we'll have you back in the future. And I think with that, we say happy array programming.
Happy array programming.
Yeah, well, we really messed the timing on that one up.
I didn't pick up on it. That's yes. It's when you say, and with that we'll say that, then I should immediately answer have array programming, and then we'll line up. But yeah, right. We'll not fix it in post.
We nailed the last couple, so it's all right to have one that's a little bit off. Thanks everyone for tuning in.